Series circuits in DC circuits, arguably two quite new concepts that students find quite difficult to grasp. Anyway, hopefully if you have a listen to what I've got to say throughout this PowerPoint presentation, you should be a little bit clearer by the end of it. Reading the slide information, 6.1, the series circuit, which we endeavour to give you a good holding on so we can move on to parallel circuits. Current in a series circuit. Well, I seem to say this continuously. The current in a series circuit is constant, but we shall work through that through the following slides. Resistance in a series circuit. Well, the total resistance in a series circuit is simply the sum of the resistors, but we'll follow that through. Voltage in a series circuit. Once again, the voltage in a series circuit is simply the additions of the individual voltage in the series circuit. Summary of the series circuit. Power in a series circuit. The power in a series circuit, or the total power in a series circuit, is simply the additions of the power dissipated in each of the loads, typically resistors. And then finally, in this at 6.7, we'll have a little bit of a discussion about faults in series circuits, which faults are being using terms like normally open or normally closed, or open circuit, closed circuit, zero resistance, infinity resistance, etc. Okay, as can be seen on the picture here, with the diagram to the left with 4 light bulbs connected to 2 batteries, and on the right hand side you can see the symbols and the electrical symbols, in which is relating to the batteries and the light globes. But you can see that the current that would flow out of the battery, excluding electron theory flow, which we all know that the electrons actually flow from the negative terminal of the batteries through to round to the positive. But we don't actually talk like that. Normally we say that the current flows out of the positive of the battery and flows through the first light, and then through the second, third and fourth light, and then returns to the negative of the battery. So the current in this circuit, if 1 amp is flowing out of that battery, you can see that 1 amp flows through all of those light globes, or all of those resistive light globes, and flows back to the negative terminal. So the way to pick a series circuit is simply to have a look and see if all the current is constant through all of the loads, then that is a series circuit. This slide is showing you that there's just over half an amp, just over 0.5 of an amp flowing through or out of R1 and flowing into R2, and there is just over half an amp flowing out of R2 and flowing into R3, and just over half an amp flowing out of R3 and flowing back to the battery. So the current in this circuit is equal. So the current flowing through R1, R2 and R3 is the same, and therefore this is a series circuit. So in the left diagram A, you can see that there is 1 amp flowing, and it's clearly showing that on the ammeter, and there is only one load, so it is a series circuit because the current in this circuit is constant throughout the circuit. And we can see now that if we add another light bulb, which we must assume has the same resistance as the first, if we add another light bulb in series, as we've done on the diagram on the right, circuit B, you can see that the current has reduced from 1 amp to half an amp. Okay, as can be seen from the previous slide, if you add an additional light bulb or an additional resistor into a series circuit, the total resistance of the circuit increases, and as can be seen here, RT is equal to R1 plus R2 plus R3, and so simply adding of each of the resistors, if you add all of those resistors together, you will come up with the total resistance. And likewise, the current here listed is I, which really should be IT, is equal to IR1, which is equal to IR2, which is equal to IR3, etc. That is simply the mathematical way of saying that the current flowing in R1 is the same as the current flowing in R2 and R3, and obviously that is also equal to the total current which is flowing out of the battery, and that indeed is the definition of a series circuit, that the current in a series circuit is constant throughout the circuit. The final formula given here, which is part of Ohm's law, I is equal to V on RT. To calculate the total current in a circuit, you could simply total current, IT, would be equal to VT, the total voltage applied to the circuit, divided by the total resistance of the circuit, would give you the total current. And once you have obviously the total current, you also then have the current through all and each of the resistors. So yeah, series circuits. So voltages in a series circuit, whilst it's quite easy just to simply say that the total applied voltage is equal to the sum of the voltage drops around the circuit, that doesn't really mean much unless you understand that each resistor, in this case R1 at 20 ohms, if there is an applied voltage, and in this case there is a DC power supply of 20 volts applied to this circuit of 3 resistors, each of those resistors has to have a voltage drop which, when added together, must equal the 20 volts, the applied voltage. I guess if we think of water flow being the 20 volts being the applied voltage, you could think that there is water flow at a pressure of 20 volts which is flowing through R1, R2 and R3, because the current in a series circuit is constant. And R1, the resistance value it's like a tap, and it's kind of turned off somewhat, and we might say it's turned off 20%. If we had a tap that was turned off at 20% and we had water flow flowing through it, you would have a pressure drop across that tap. Well, that pressure drop is, if you like, the voltage dropped across that resistor. So the water flow diagram or theory does work quite well, and of course that if the total pressure drop across that series circuit is 20 volts or 20 psi or whatever we measure water in, but it's 20. Obviously the total pressure drops around the circuit have to equal the applied pressure. So getting back to electrical, if we have a 20 volt supply and we have 3 resistors, the sum of the voltage drops, that being V1, V2 and V3, must equal 20 volts. So moving on, if we knew that we had the voltages across R1, R2 and R3, but we didn't know the applied voltage, we could simply add V1 plus V2 plus V3 equals the applied voltage. As you would expect, when you add up the voltage drops in the previous example, you get 20 volts, which is the supply voltage. This is called Kirchhoff's voltage law, after Mr. Kirchhoff, a German physicist, who said, the algebraic sum of the voltage drops in a series circuit is equal to the applied voltage. This law is important, or is as important as Ohm's law. Like Ohm's law, it can never be wrong. The voltage drops around a series circuit can never total any more or any less than the applied voltage. The next two examples show how Kirchhoff's law voltage works. By calculating the current in this circuit, shown by the scribbly black text on it, if we have 10 volts across a 100 ohm resistor, we can work out that there is 0.1 of an amp flowing through that resistor. The interesting thing here is that within a series circuit we should also understand that the current in a series circuit is constant, so therefore all other resistors in that circuit would also have 0.1 of an amp flowing through them, and if you knew their resistance value, you could calculate the voltages across each of those resistors, and knowing Kirchhoff's law, once you have calculated the voltages across all of the other series resistors, you could simply add those together and you would have the applied voltage, or the total voltage. This is the game of chess that that I talk about anyway. This slide is just making you aware that Kirchhoff's law states that you add the voltages algebraically, which means that you have to consider the polarity of the voltage. This only is a concern if there are more than one supply voltage to a circuit. Really, in our situation and most situations, this is not required to be taken into account, but do realise that if there are two power supplies on one circuit, there is an interaction between the way voltages interact. For instance, if you were to have, say, 10 1.5 volt cells and you connected them in series, you would have 15 volts as a total voltage. If you, that's 10 times 1.5. if you added them, if you connected them positive to negative, and so on. But if you accidentally or for some reason decided to turn one of the batteries around and one of the batteries was connected positive to positive and negative to negative, that would take away from the total 15 volts. Probably not making myself too clear there, but just trying to explain the word algebraically and polarity. So to find the voltages or the voltage drops around a circuit using Kirchhoff's law, in the first dot point, if we were trying to calculate the voltage drop across the last resistor, if you like, on the right hand side, the V question mark, probably should have labelled that VR3, but nevertheless we can see that the applied voltage or the supply voltage is at 100 volts, and the voltage drop across the first resistor is 50 volts and the second resistor is 10 volts. It should be quite clear now that if you wanted to calculate the voltage across the V question mark, the answer to that would simply be 40 volts, and that is because, however you want to work it out, transposing formulas or doing whatever, which all sounds very difficult to me, but you should be able to realise that 50 volts plus 10 volts is 60 volts. So 60 volts plus what equals 100? Well, the answer to that is 40. So the voltage across the V question mark, if that was 40 volts, it would be 40 volts plus 10 volts, which is 50 volts, plus 50 volts is 100 volts, and the supply voltage is 100 volts, so therefore the sum of the voltage drops around the circuit is equal to the applied voltage. Okay, so having a look at some typical faults, and this one being an open circuited fault. Open circuit obviously means that well, in this case, the filament in the light bulb has blown apart, so there is no connection. Open circuit equaling a very high resistance, so the filament is opened up. If the filament opens up and there's no connection between through the light bulb, there is no current flowing because the current can't go through the open circuit part of the light bulb, so the current falls to zero. And obviously in this case, if the current falls to zero, all 4 lamps will go out. So and obviously then the 12 volt supply, the VT, the voltage supplied to this circuit is 12 volts. You would have a voltage reading as shown by the voltmeter across the open circuited filament of 12 volts. This particular fault, being a short circuit, is where the filament in the lamp, I must say, is highly unlikely to ever actually do this, but at the end of the day they're suggesting here that the filament has internally shorted out. If you like, someone has taken the glass off the globe and twisted the the wires inside the lamp together, so there is no resistance across that lamp. So in this case, the voltage across the short-circuited lamp would be 0 volts, and the current would be able to flow through it. And in fact, you should realise that were that lamp operating correctly, the lamps would have been at let's say 100% brightness, and with that lamp now being short-circuited, that resistance is 0 ohms, and so the total resistance of the circuit would be slightly less than, in fact it would be 25% less than it was, and therefore with the resistance being 25% less, the current would increase somewhat, a small amount, well 25%, and those lamps would now be operating at 125% of their original brightness. Probably likely for those lamps now to start popping, and the next lamp hopefully would go open circuit. But yeah, this circuit here is I think trying to suggest that the switch in the circuit is getting hot and is actually starting to burn the contacts, which would ordinarily make that resistance of the switch low, like 0 ohms when it was turned on, and the current flowing through to the 2 lamps would all, of course, flow through the switch provided. If there's too much current flowing through that switch, it is possible that the resistance of that switch could increase. Maybe not enough to go open circuit. If it did go open circuit, of course the lamps would go out. But if the resistance started to change from 0 ohms to 10 ohms, 20 ohms, 100 ohms, you would see the light starting to dim as the total resistance of the circuit would have to take into account the resistance across the switch, including plus the resistance of lamp 1 and lamp 2. So sometimes you might see some lamps sort of getting dimmer and brighter and dimmer and brighter. That will be typically due to a loose connection or a faulty switch and its resistance changing.